Simine Vazire. She is Associate Professor of Psychology at Washington University and the Rosenzweig Chair in Personality Science. And she's going to start us off for the day.
Thanks so much, Michael, for putting this together.
Yeah.
For inviting me. I'm really glad to be here. I'll tell you a little bit about my background, what I do, and why I'm here, although I'm not sure I know why I'm here. So I'm a personality psychologist. I do correlational and longitudinal research mostly. I teach our graduate research methods class at WashU in the psychology department. I'm on sabbatical right now, which is awesome. And I also am an editor for a few different journals, so I handle a lot of papers and see reviewers' comments and things like that through that. So I've learned some things from editing and from teaching graduate research methods and so on. And what I'm going to talk about today is a little bit of background. So for some of you, this will be really boring, and I apologize. I'll talk a little bit about null hypothesis significance testing, a little bit about what's wrong with it, why power matters, how we don't have enough power, how people compensate for the lack of power by doing something we now call p-hacking, how you can detect p-hacking. So this is useful if you're reading psychology articles to know how reliable the results are, and some solutions, whether you're consuming research or producing research yourself, what are some kind of the major things to look out for. And so just to give a little bit of context, the field of psychology is going through this huge flux right now where there's a lot of people saying we need huge reforms in our research methods. The way we've been doing things is bad and causes a lot of false positive results. Our research is not replicable, or a lot of it is not replicable. Some people don't think that's the case and think everything's fine, we don't need to change. I'm in the camp that do thinks we need to change a lot, that a lot of our practices are not good. This is somewhat related to the fraud that has happened in psychology, but only tangentially. There's some overlap in the bad practices that we've been teaching our students and doing, and then the connection with the fraud, although I think there's huge differences too. So I want to make that distinction that the stuff I'm going to be talking about, like p-hacking, some of the practices that are not ideal that people still do and that we still teach our students are not considered fraud, and I don't think they should be considered fraud, but we should be moving away from those such that maybe eventually they would be considered unethical to continue doing those things. So I'm hoping to give you guys both some background in kind of the traditional way that psychologists do research and analyze their data and so on, and then some of the bad practices we've done to try to encourage you guys to do better than us and to know when you're reading research what's a solid finding and what might not be replicable. So some background. I'm going to use an example throughout the talk, and I don't mean to pick on this paper, especially since we're streaming live. I definitely don't mean to pick on this paper. This is a paper published in Psychological Science, one of the leading journals in psychology this year. Part of the title was Acetaminophen reduces compensatory affirmation following threats. So this is the table from, or the graph from one of their studies. What they had was the dependent variable. What they asked participants to do was rate how much they would punish a hypothetical person in a hypothetical scenario. They had a control condition where they just read the scenario and said how much they would punish the person, and then they had a mortality salience condition where before they read the scenario and said how much they would punish the person, the idea of mortality was primed for them. They were made to think about their own death, and that's supposed to be a threat. So that's what following threat means. And then compensatory affirmation is supposed to be punishing somebody else. So the idea is that this is, you compensate for this threat you feel by punishing other people more. And that argument is that taking Tylenol reduces how much people do this. So what they found was in this mortality salience condition, people who took Tylenol punished less than people who took a sugar pill, a placebo. And there's also a control condition where they showed that that had no effect if you didn't threaten people. But for simplicity's sake, we'll just focus on this experimental condition where they said that they found that people punished more if they didn't take a Tylenol than if they did after being threatened. This is the graph from study 1. There were 40 people per cell, so 40 people in each of these 4 conditions. That's a small n, means that that's a number per cell, per condition, instead of total. And they found an effect size, Cohen's d, of 0.52. We'll talk a little bit more about what that means. Study 2, similar results, similar study, similar design. Okay, so how should we decide whether to trust this finding, whether to believe it, whether to build on it, build theory off of it, and so on? Well, let's talk a little bit about how we come to these kinds of graphs, these kinds of conclusions. So some basic assumptions that we believe that when we're doing psychological research that there's a true effect size in the population. It might be 0, it might be very strong. And effect size is the actual difference between the groups if you're comparing different groups, or the actual correlation between two variables if you're doing correlational research. It's the actual association between two variables, an independent variable and a dependent variable, for example. And so we believe that there is some truth about what that effect size is. It might be 0, it might be very strongly positive, very strongly negative, but there's some truth and we want to try to get at it. We can't directly measure it, we have to infer it from a sample, so neither can we directly measure the variables we're interested in, we have to operationalize them into a Likert scale or something like that, and we also can't sample everybody in the population we're interested in, so we have to take a subsample and then do inferential statistics from that subsample. And there's error in our measurement. This is a really important part of inferential statistics, is that we have to account for the fact that there's error in our measurement, they're not precise, they're not exact, and we shouldn't take them that way. Okay, so the goal is to draw the correct conclusion about whether the effect is 0 or non-zero. So if we're talking about the difference between the two groups, say the group that took Tylenol and the group that didn't take Tylenol before they were threatened by thinking about their own death, we want to know, is the difference between those two groups in terms of how much they would punish somebody 0, or is the difference between the two groups not 0? That's one of the things we want to draw a conclusion about. We also want to know the direction of the effect. So does the group that took Tylenol punish less than the placebo group, or do they punish more? And ideally, we would like to know the approximate magnitude of the effect. So how does that effect compare to other, the effect of, say, having someone tell you they love you right before you decide whether or not to punish somebody, or other things that people might manipulate or might happen to somebody before they have the opportunity to punish somebody. Now, in practice, so in theory, these are all the things we want to draw correct conclusions about. In practice, because we use what's called null hypothesis significance testing, really what we're testing is whether the effect is 0 or non-zero. We're not actually really getting a measure of how correct we are in our conclusions about the direction of the effect or the approximate magnitude of the effect. And that's one of the big criticisms of null hypothesis significance testing, is it's very black and white. It's just, do you think there's an effect or not? And then we kind of ignore the magnitude of the effect, the direction we get from our theory, right? Our theory tells us which direction the effect should be. We hope we're right. But the magnitude of the effect we kind of ignore. We just say, well, it's either significant or it's not. It's very dichotomous thinking. But really, we should care about those things. Okay, so how do we draw correct conclusions or more correct conclusions? Well, with null hypothesis significance testing, we calculate the probability of observing the results we did observe if the true effect size in the population is 0. And that's what the p-value you get from your statistical analysis tells you. It tells you the probability that you would have observed those results or more extreme results if, in fact, the true effect size in the population, the true difference between the groups, is 0 in the population. So things that influence your obtained p-value are the magnitude of the observed effect. So in the Tylenol example, how different the Tylenol group versus the placebo group was in terms of how much they punished, how far apart those two means were, the amount of error in measurement, and the number of observations. And we'll get back to that. Okay, so in this example, the difference between the means, that's one of the things that affects the p-value, is how different these two means were, ignoring the control condition for now. Another thing is how much error there was in the measurement, and that's what these error bars are a reflection of that. The more error there was in the measurement, the less different, right? The larger the p-value, that is, the less we're likely to conclude that these are significantly different from each other. And then the sample size is another thing that influences your p-value, how likely you are to conclude that they're significantly different from each other. Okay, so null hypothesis significance testing starts with the assumption that the null hypothesis is true. It starts with the assumption that in the population, the real effect is 0. Of course, we want to end up with a different conclusion than that, but null hypothesis significance testing, every p-value derived under this framework starts with this assumption. It only tells you about probabilities in this reality. So you ask the question, how likely is it that I would have observed an effect this size or larger if there actually is no difference in the population? Okay, so let's break this down. So how likely is it that I would have observed an effect this size or larger? So first, let's talk about the effect size. That's the difference between the two means, for example. If you're doing an experiment where you have different groups, like in this Tylenol example, the standardized measure of effect size is called Cohen's d. Sometimes you just see the d. It's never capitalized. It's always lowercase. And I'll give you some rules of thumb for how big you should expect the Cohen's d to be. If you're doing correlational research, you get an R, lowercase also. F values and T values are not effect sizes. Along with other information, they can be used to compute effect sizes, but they themselves are not effect sizes. There's other kinds of effect sizes besides Cohen's d and R, but those are the most common. So what's a large effect? We'll get back to this, but in Cohen's d terms, usually 0.2 is considered small, 0.5 is considered medium, and 0.8 is considered large. In either direction, so it could be negative 0.2, negative 0.5, negative 0.8. Those are small, medium, and large. In R terms, it's about, you can divide Cohen's d by 2 roughly, and you get R. It's not quite a linear transformation, but especially at low levels of d and R, that works. So that would be, a small R would be 0.1, a medium R would be 0.25, and a large R would be like 0.35. Okay. Now let's take this part, the how likely part. So this is a matter of probability. So we assume, right, we're under null hypothesis testing, we're assuming that in the real population there's no effect. There's an effect size of 0. Now if you take a sample from that population and you look at the difference between the two groups in that sample, sometimes that sample is going to have an effect size different than 0 just by chance, right? You just happen to pick people who in the acetaminophen condition punished less, but not because they took the Tylenol, just by chance they were randomly assigned to that condition. So sometimes by chance, you'll get an effect size of 1 or 2 or -1 or -2, usually not this far out. If the true effect is 0, usually it'll be pretty close to 0 in either direction. And so you can calculate, let's say I get an effect size of 0.5, what's the probability that I would have gotten an effect of 0.5 or larger if I'm in this distribution where the true effect is 0. So it's basically the area under the curve from here on out as a percentage of the total area under the curve. So to get a small p-value, you have to be further away from 0. Your observed effect size has to be pretty far from 0, or you have to have very little error, or you have to have a large sample. So all those things kind of influence each other, influence the p-value. Okay, and so just to reiterate that this is assuming no effect in the population. So again, I want to emphasize that in actual research, you're dealing with a sample, but you're inferring to a population. Okay, so what does a p-value mean? There's a lot of misunderstanding about what p-values mean. There's been studies where they survey people who teach statistics and give them multiple choice questions about what p-values mean, and still a significant proportion of them get it wrong. So a p-value does not mean any of these things. It does not mean that if you get a small p-value, say 0.03, which is, you want small p-values. Smaller is better with p-values. If you get a p-value of 0.03, it's less than the magic 0.05. What does it mean? It does not mean the null hypothesis is false. It does not mean there's a 3% chance that the null hypothesis is true. It does not mean there's a 97% chance that your alternative hypothesis is true. It doesn't mean that if the study were repeated, you would get a significant result 97% of the time. It doesn't tell you about the probability of replication, or it tells you something, but it doesn't tell you exactly, you can't convert it exactly into a probability of replication. What it means is that assuming the null hypothesis is true, the probability of observing an effect is larger than the one you observed is 3%. Hopefully I've repeated that enough times. Okay, so a table we commonly use when we teach about null hypothesis significance testing is this one, where you have the reality. In one reality, the null hypothesis is true. In the other reality, the research hypothesis or the alternative hypothesis that there is a difference between groups is true. And then you have the conclusions that you draw. You either draw the conclusion that the null hypothesis is true or that the research hypothesis is true. So if you're in the reality where the null hypothesis is true and you conclude that the null hypothesis is true, that's a correct rejection, right? That's good, you made the right conclusion. It's bad because you can't publish it, because it's not significant. The null hypotheses are not interesting, right? That's how we tend to think, that they're not worth publishing. But if you're in the reality where the null hypothesis is true in the population, but you conclude because of your data that the research hypothesis is true, you've made a type 1 error. Now, remember, in null hypothesis significance testing, all the probabilities we get, the p-values, only tell us about this world. It assumes we live in this world. And we can control what our type 1 error rate is in this world by setting alpha, which is the critical p-value we deem necessary in order to consider something significant. And in psychology, that's 0.05. So we're deciding, we're tolerating a 5% error rate in terms of concluding, in terms of falsely concluding that null hypotheses are false. when in fact they're true. So that tells us when in fact the null hypothesis is true, 5% of the time we will conclude that it's false. And that will be a mistake. And different fields use a different alpha level. Like medicine sometimes uses 0.01. So depending on how much you want to tolerate false positives, you can change your alpha level that you use. But psychology uses 0.05. Now that doesn't tell us about the error rate in all of psychology, because there's also the other kind of error, right? So you could be in the world where the research hypothesis is true, in which case if you conclude that the research hypothesis is true, that's a correct conclusion. But if you conclude that it's false, that the null hypothesis is true, then you've made a type 2 error. And so there's both kinds of errors in the literature. Of course, the psychology literature only consists really of these two boxes. You don't see a lot of papers that conclude that the null hypothesis is true. Almost every single published study, I think it's over 95% of published studies, conclude that the research hypothesis is true or reject the null. So really, if you want to know the error rate in published studies, you need to know the proportion that are in this category versus this category, and we can't know that for sure. We can infer it, but we can't know that for sure. So it's false to say that at most only 5% of research findings are false positives. That's not the case, because that's comparing this proportion to this proportion. But what we really want to be doing is comparing this proportion to this, the bottom half, and that's a very different question. I'll get back to beta and power later. Okay, so a few conventions, and stop me if anything is unclear. Of course, I meant to say that earlier. So p-values, we tend to report if it's greater than 0.10, we just say it's not significant. Sometimes people give the exact p-value. Now APA, the American Psychological Association, is saying that we should publish exact p-values when we report results. And I think it's a very good change in the right direction. Exact p-values are useful. If it's less than 0.10 but not less than 0.05, we give it a cross. I couldn't find the cross symbol, so I put a plus sign, but the symbol we use is a cross, and we call it marginally significant. If it crosses a 0.05 threshold, it's less than 0.05, because that's our critical p-value, our alpha that we've decided as a field to use. We call that statistically significant. We give it 1 star. And then if it's less than 0.01, sometimes we give it 2 stars. Less than 0.001, sometimes we give it 3 stars. People use these 2 and 3 stars differently, so you want to be careful how you interpret that. But that's often how they're used. Okay, now I want to show you, I have a few more conventions. So effect sizes I mentioned, small is d of 0.2, medium is d of 0.5, large is d of 0.8. Here are the corresponding R values. The average published effect size in social and personality psychology is an R of 0.21 or a D of 0.43. So that suggests that maybe calling 0.5 medium and 0.8 is very, very large. There's very few studies in psychology that find Ds of 0.8, except in very small sample research, and you'll learn about why that is later. So fMRI research, for example, will almost always have huge effect sizes. And then confidence intervals, which we'll get to later, the convention is to report a 95% confidence interval. Sometimes you see different ones, but 95% is the most common. Okay, so, and then power, which we'll talk about later, the convention is to have 80% power. And we'll come back to that. At minimum 80% power. Okay, so the next thing I want to do is show a video. This is a critique of null hypothesis significance testing by Jeff Cumming, who's a methodologist in Australia. He's now retired and is kind of making it his mission in retirement to try to spread his critique of null hypothesis testing and his alternative view, which is to focus more on effect sizes and confidence intervals. This is a 9-minute video.
Psychology and many other disciplines rely on the p-value to interpret data. But can we trust p? You might think of p as the strength of evidence. There's an effect. Lower the p, stronger the evidence. There's language to talk about p-values. Less than 0.05, significant. Between 0.05 and 1.0, approaching significance or running away from it. This language suggests truth. 3 stars, an effect exists. Greater than 1.0, it doesn't. Think how you feel. 3 stars, yay, between 05 and 10, frustration, so close. And P really matters. 3 stars, fame, greater than 05, a waste of effort, maybe no PhD. So the p-value determines what we believe and what gets published. Does it deserve so much faith? If P reveals truth, a replication should reveal the same truth, so give roughly the same P. Or we could ask, is P a reliable measure of strength of evidence? If so, repeating the experiment should give about the same P. Our basic question, if you repeat an experiment, how much will P vary? If P deserves our trust, the answer needs to be not too much. Let's mark the moods of p-values. 3 stars, jump for joy, bright red trumpet. 2 stars, upbeat clarinet. 1 star, okay. Between 05 and 10, question mark, a bit blue, trombone. Greater than 10, blue depression, deep trombone. Now the simulation, to see how P varies as we repeat an experiment. Suppose your pep-up therapy increases well-being scores by 10 on average. Here's the control population, mean 50, and the experimental population, mean 60. Each is normally distributed, standard deviation 20. Population effect size is 10, that's half a standard deviation.
That's a
so standardised effect size, delta, equals 0.5, a medium-sized effect. Our control and experimental groups each have n equals 32. Run 1 experiment. The blue dots mark the scores for 32 control participants. Here's their mean and 95% confidence interval. Here are scores of 32 pep-up participants and their mean and confidence interval. We focus on the difference, so here's a difference axis, 0 lined up with a control sample mean. The green dot marks the sample difference, and here's the confidence interval from that difference. This experiment estimates the effect of pep-up to be about 15. Another experiment, first result drops down, and the second estimates the effect to be just a little more than 15. Run repeated experiments. This dotted line marks 10, the true effect of pep-up. These intervals bounce around, and in the long run, about 95% will capture the true value. Just the occasional one, such as here, will just miss. Now, p-values. Run an experiment. Here's its two-tailed p-value. The confidence interval does not include 0, so p is less than 0.5. Another experiment, the interval does include 0, p is greater than 0.5. Run many experiments and look at these p-values. They're anywhere from 3 stars to 0.48, 0.58. It seems you can get just about any p-value. We'll collect a lot of p-values into a frequency histogram to study how p varies with replication. The latest experiment gives 1 star, marked by this highlighted square in the 1 star column and this small figure. Here's the distribution of p-values. They vary across the full range from 3 stars to greater than 1.0. The statistical power is 0.52, meaning in the long run, 52% of experiments give p less than 0.5, so the 1, 2 and 3 star columns will total 52%, as they pretty much do. You might suspect trickery. Have I chosen some weird extreme case? Absolutely not. 2 groups of 32 is quite large for psychology. 0.5, a solid medium-sized effect. Also, studies have found that in many areas of psychology, the median power of published research to find a medium-sized effect is about 0.5. My simulation is typical for much of psychology. Doing a typical experiment amounts to closing your eyes and choosing a random interval from those on screen, a random p-value from the column here. It's p-value roulette, and the histogram gives the probabilities of the different outcomes of a spin of the p-roulette wheel. Let's visit the p-value casino. Say when you want to stop and see what result your experiment gives. Oh dear. Oh dear. 2 stars. Getting 2 or 3 stars may be more a matter of luck than skill. Here's another way to illustrate how p varies for our typical experiment, the dance of the p-values. The conclusion has to be that p is a highly unreliable measure. Whatever the p you obtained, it could easily have been very different just by chance. For a typical experiment, p tells you virtually nothing. You simply can't trust p. Here's the histogram for power 0.52. Change the population effect size delta and see separation between the distributions, power, and histogram all changing. This ESCI simulation lets you play around with features of your experiment and see how the distribution of p changes. In just about every realistic case, p-values show dramatic variability. With effect size 0.5, vary the sample size and see power and the distribution of p changing. With n equals 62, large samples, power is 0.8, often considered acceptable power. The dance of the p-values gives more trumpet, but still p-values jumping all over the place. Would you like your tenure dependent on winning this version of p-roulette? Back to our typical experiment. Of course, a real-life researcher doesn't know about the populations or the true size of the effect and has only a single experiment. But now, in your mind's eye, you know about the infinite sequence of experiments. Which gives a better idea of the infinite set, your interval or p-value? I suggest knowing one interval does tell you about the whole infinite set. Its width gives some idea of how much the means bounce around with replication. In dramatic contrast, a single p-value tells you virtually nothing about the whole set. It's simply one value chosen randomly from the histogram, which has enormously wide spread. A confidence interval is much more informative than a mere p-value. Medicine adopted confidence intervals more than 20 years ago, and meta-analysis to combine evidence over studies. We shouldn't let p control our research decision-making. It's simply not reliable. You just can't trust p. Here's psychology struggling out of the p swamp into the promising garden of confidence intervals.
So as Jeff mentioned in the video, we don't actually know the true effect size in research, right? In that simulation, he just postulated that the effect size was 0.5, a d of 0.5, and then you could manipulate the sample sizes to come up with these simulations that tell you. But the key thing is that if you increase the sample sizes, right, then the effect estimates become much closer to the true effect size. The confidence intervals around those effect estimates shrink, and the p-values become more consistent. So that's one key thing, is that by increasing sample size, all those wonderful things happen. If you increase the true effect size, that also has those good consequences. So if you're testing an effect that in reality, you can't know this, but if in reality the true effect is quite large, then you're going to get more consistent results and narrower confidence intervals and so on. So you can try to study large effects, but that's really hard to do. We don't know which effects are large a priori. And if you're studying complex interpersonal or behavioral phenomena, you're not going to get huge effects almost no matter what. But one thing you can do is increase your sample size, and we'll come back to this a lot. Okay, so why power matters? So power is if we go back to, is this what I have next? Let's see. No. Okay, I'm going to go back to, yeah, here. So power is your probability of concluding that the null is false, or accepting your alternative hypothesis, if in fact that's the right conclusion. So if you live in the world where your research hypothesis is true, lucky you, and you conclude that, then that's great, and your probability of doing that versus incorrectly concluding that the null is true, that's power. So it's the inverse, or 1 minus the probability of making a type 2 error when you live in this world, right? So hopefully we're most of the time in this world where our research hypothesis is true and the null is false. Hopefully we have good intuitions and good theories, and we're testing hypotheses that are true and not null effects. And we want to maximize the chance of correctly concluding that instead of incorrectly saying, oh darn, the null looks like it's true. I guess I can't publish this. And so we want to maximize power and minimize the probability of a type 2 error. Okay, so that's power. And as Jeff Cumming mentioned, the typical kind of standard for power is we say you should have about 80% power. In grant proposals, they want to see that you calculated how many people you would need in your study to have 80% power. Now, 80% power doesn't mean anything unless you link it to a specific effect size. You need to have 80% power to detect an effect of X magnitude. Now, if you change that X, how big your effect size is, then what sample size you need to achieve 80% power is going to change. So if you have a large effect size, you don't need a lot of people to have 80% chance of detecting that large effect. If you have a small effect size, you're going to need a lot more people in your study to have 80% chance of detecting that small effect. Small effects are harder to detect, right? If you think about a confidence interval, right? If your effect is close to 0, that confidence interval is going to include 0 more easily than if your effect is far away from 0. So the closer to 0 your true effect is, the narrower you need your confidence interval to be to not include 0. And to get a narrow confidence interval, you need more people in your study or more observations. So I'm using sample size interchangeably with number of people in your study. There's some designs where that's not, your sample size is actually not the number of people, but the number of observations you have for each person, or some combination of those. I'm just going to simplify, assuming it's a between subjects design or a correlational study that's between persons, which a lot of social and personality psychology is, but in other sub-areas that's not necessarily the case. But for now, we're just going to assume sample size is number of people, and if that's not the case in your area of research, you can just adjust in your mind. Okay, so why power matters. So you have more precise estimates. So I used Jeff Cummings' free, so that simulation he did was in Excel. He wrote a macro. You can download it for free. He has a bunch of other Excel sheets. I made these graphs with his software. So here is a case where we have an effect size of 0.4. So about the average effect, D of 0.4, about the average effect size in social and personality psychology, and a standard deviation of 1. And if I have 10 people per group in a 2-group study, and I estimate, in all my simulations, I assumed I got the exact right point estimate of the effect. So I got a point estimate of 0.4, but my confidence interval, my 95% confidence interval, is huge, right? It goes from minus 0.5 to 1.3 or something like that. So the 95% confidence interval is roughly, we're 95% sure the true effect is somewhere in this range. If I only have 10 people per cell, I have no idea where the true effect is. Even if I estimate it exactly right on, it turns out I can't be very sure because I have such a small sample that it's hard to infer from that sample to the population. If I increase my sample size to 20 per group, so 40 total, my confidence interval shrinks a little bit, but it still includes 0. I still don't know, maybe the effect is 0, maybe it's even a little negative, maybe it's huge, maybe it's medium. But then as I increase the sample to, say, 80 per group, now I have a confidence interval that doesn't include 0, but I still don't really know. It could be a small effect, it could be a pretty large effect, right? So I'd have to get to a pretty large sample size to have a really accurate estimate of the magnitude of the effect. Now, in psychology, we typically don't care too much about having a very accurate estimate of the magnitude of the effect. We just care about knowing that it's not 0. So, about 60 people per cell would be enough for an effect size of 0.4 to have a 95% confidence interval that doesn't include 0 if your study gets the right point estimate, which it may not, right? If I ran the study again, I may not get a 0.4 point estimate. I may by fluke get a point estimate much larger or smaller. Okay, but if you have more people per group, you're going to have a narrower confidence interval. You're going to be more likely to be able to conclude that your effect is different from 0, and also be more sure where it is on the scale, on the spectrum, from small, medium, to large. So if we're thinking about maximizing the number of correct hits relative to type 1 error, by increasing power, we're tilting the balance in favor of correct hits and hopefully fewer type 1 errors. Now, it also helps when you're actually testing a hypothesis that turns out to be false. You're studying a question where the null is true. There actually is no difference between groups. It still helps to have a lot of people, a lot of power, a lot of people in your sample. So let's take that case where the actual effect is 0. I observe an effect of 0. If I have 10 people per group, my 95% confidence interval tells me the effect is somewhere between very large and negative to very large and positive. So I really don't know anything more than I did before. I still have no idea where the real effect is. As I get more and more people per group, I get more and more sure that the true effect really is pretty close to 0. Although even with 100 people per group, you see the 95% confidence interval goes to minus 0.3 to plus 0.3. So there could still be a small effect there. I'd need even more people to rule out the possibility of a small effect. So especially when you want to draw a conclusion about no difference, you need a really narrow confidence interval. If you just want to draw a conclusion that there's no big difference, right, then you could have a more medium-sized sample. But if you want to be really sure that there's no effect at all, you need a very, very large sample. Okay, so with more power, you don't actually make less type 1 error, but you make less type 2 error, and your proportion of correct hits to type 1 error goes up. So that's a good thing. You have fewer false positives as a proportion of the literature. Okay, and less wasted time and money. So one thing with small sample studies is that if they're uninformative, if they give you large confidence intervals and you don't really know if there's no effect or a large effect or a small effect, you just wasted all the time and money that went into doing that study. You're no better off, or they're only a tiny bit better off having that evidence than before you had that evidence. So an important reason why people should run larger studies, even though it costs more and it's more time intensive, you actually learn something, right? So at least that time and money went into producing knowledge. Okay, so how much power should we have? So I'm going to show you some slides from another talk that Joe Simine gave at SPSP last year. He's one of the authors. You may have heard there was a paper that came out in Psych Science a few years ago called False Positive Psychology that did a simulation to show that you can get false positives very easily by using certain research practices I'll talk about later. So Joe Simine also gave a talk at SPSP this last year, which is our Social and Personality Conference. In their original paper, Simine and his colleagues recommended a very small number of participants per condition in experimental studies. And so then they later decided to rethink this and think, well, how many people do we actually need per condition to draw good conclusions, solid conclusions from our research? So these are some of his slides. So everything below here is from Simine's SPSP talk. He posted his slides publicly. I hope he doesn't mind me using them. So lots of published studies have 20 or fewer observations per condition. If it's a between subjects design, that means people per condition. They recommended getting more than 20, and he says this is ridiculously low. So even saying a minimum 20 is way too low. So how do we know that? Well, they did a study to see what can you reliably detect with 20 people per condition. So to have 80% power, you need to be studying an effect with Cohen's d of 0.9 or greater, or a correlation of roughly 0.4 or greater. And so their question was, well, what effects out there are actually that big? So they tested some quote-unquote obvious hypotheses on mTurk, so they got a very large sample, almost 700 people, to get estimates of true effect sizes. Because with 700 people, you can have a really narrow confidence interval and be pretty sure that your observed effect size is very close to the true effect size. So they could find out some of the true effect sizes of some obvious effects and see whether they're actually 0.90 and so on. So men are taller than women, you can detect with 6 people per condition. That means 6 men and 6 women. That's enough power to detect the effect size difference between height and men and women. So it's a large effect, very large effect. Anything you can detect reliably with 6 people per condition is a huge effect. People above the median age report being closer to retirement. You can detect that with 9 people per condition. Now you see why these are obvious hypotheses. Women report owning more pairs of shoes than do men. 15 people per condition, 15 men, 15 women. You get reliably correct conclusions about that. What can't you reliably detect with n equals 20? People who like spicy food are more likely to like Indian food. You need 26 people per condition. So think in your head about some of the psychological theories that we test compared to this theory, right? Our theories are probably a little bit less likely than this theory. Liberals rate social equality as more important than do conservatives. You need 34 people per condition. Men weigh more than women. You need 46 people per condition. People who like eggs report eating egg salad more often. You need 48 people per condition. So he focused on this one. Oh, sorry. Smokers think smoking is less likely to kill someone than do non-smokers. 144 people per condition. That's a very small effect. So actually, smokers and non-smokers are pretty similar in terms of how likely they think that smoking is to kill you. Okay, so he focused on this one. Men weigh more than women. You need 46 people per condition. Are you studying a bigger effect than men weigh more than women? Is your psychological effect about It's a psychological theory about the effect of acetaminophen on reducing meaning threats and its effect on then how much you punish other people, a bigger effect than the difference in weight between men and women. Or if you don't like that one, if you don't have an intuition about how much men and women weigh, how about liberals rate equality is more important than do conservatives, or people who like eggs report eating egg salad more often, right? How many of our psychological theories really are likely to have bigger effects than these things? Not very many, right? In fact, our theories, our effects that we're looking at, are likely to be quite a bit more subtle than these. So if we have less than 46 people per condition, or really I would argue less than 70 or 80 people per condition, we're underpowering our studies. We're not drawing very reliable conclusions. We're having huge confidence intervals, or in that world that Jeff Cumming described of dancing p-values. So going back to the acetaminophen study, they had 40 people per condition in one and 50 in the other. So that's roughly what they would need to reliably detect the difference between men and women in weight. Is it enough to reliably detect the effect of Tylenol on compensatory affirmation following threats? I find that a little bit hard to believe. Okay, so another way to decide how big of a sample you need is you can use a free software called G-Power, where you put in what kind of test you're doing. Are you doing ANOVA, between subjects experimental design? Are you doing a correlation? Are you doing a regression? Are you doing a chi-square? It works for a lot of different kinds of tests. And you can either calculate how many people you need in your study in order to have 80% power to detect an effect of, say, D of 0.5, or you can change any of those parameters, right? You can say, if I think my effect, or if I want to be able to detect an effect as small as, say, D of 0.2, how many people do I need to have 80% power to do that? Or if you're reading a study and you want to say how much power did they have, so you read a study, they have a total of 80 people in their study, and they're studying an effect in social and personality psych where we know that most effects are around D of 0.4. You can say, well, how much power did they have to detect a D of 0.4? So you can do it either way. You can calculate the power based on your sample size and effect size, or you can calculate what sample size you need based on your effect size, anticipated effect size, and how much power you want, and so on. It's really nice software. And it's free. So here I graphed the sample size you would need to have 80% power to detect various effect sizes, Cohen's D. So if we want to detect the Cohen's D of 0.4, the average effect size in social and personality psych, we need about a total sample size of 190. So that's, divided by 2 if you have 2 conditions, etc. So this is for 2 independent means, 2 groups between subjects design. If you're doing a correlation, if you want to detect a correlation about 0.2, same thing. You need about 190 people to have 80% power. Yeah.
I was just wondering, is it assumed that the population is infinite or arbitrarily large? How big is the population, I guess,
or does that matter? What assumptions are made about that? I don't know if that matters. Anything else? I don't know. Yeah, yeah. I think if you have a pretty small population, and you can actually sample a really high proportion of them, then that changes everything. So it's definitely assumed that the population is much larger than your sample.
Really big, so.
Yeah. Yeah. And if you can actually sample everybody in your population, if say your population is people who are on the Apollo 13 mission and you have access to all of them, then you don't need inferential statistics at all. Okay, so how much power do we actually have? There have been several papers that looked at the typical amount of power in published psychological studies. I have a paper under review. Well, it's been rejected several times now. It will soon be under review again with Chris Fraley, where we looked at the median sample sizes for 6 different empirical journals in social and personality psychology. So these are acronyms for the journals: Journal of Personality, Journal of Research in Personality, Personality and Social Psychology Bulletin, Journal of Personality and Social Psychology, Journal of Experimental Social Psychology, and then Psychological Science, which is broader, but we just looked at papers in the field of social and personality psychology and psychological science. We coded the median sample size at different years by selecting a random subsample of the articles. We didn't code every article. We called it the NPACT factor instead of the impact factor, so NF stands for that. So this is the median sample size across the years for each journal in order. So Journal of Personality has the most with 178 people per study, and Psych Science has the fewest with 72 people per study. If you convert that into, okay, well, how much power did each of these studies have to detect the average effect size in social and personality psych, so a D of about 0.4. In Journal of Personality, they had about 77% power, in Psych Science, 40% power. So again, maybe some of these papers are setting much larger effect sizes than 0.4, but on average, that's the effect size, and that's probably an overestimate, because that's the average published effect size, and there's publication pressures that lead to inflated estimates of effect sizes. So these studies, for the most part, are not adequately powered. Even the very top journals, Psych Science and JPSV, are publishing massively underpowered studies. So it gets worse because many of these papers have multiple studies. You might say, oh, that's a good thing, right? Because if they get a false positive in one study, that's a problem. But if they did it in 3 or 4 studies, then it must be true, right? Well, not if those 3 or 4 studies are each underpowered. And Uli Shimak, who's a methodologist at the University of Toronto, has a really nice paper where he talks about total power, which is the idea of what's the power for a set of studies in an entire article. So if an article has 3 or 4 studies, what was the power of that set of studies to detect a real effect? So he graphed that. Okay, so total power, right, goes up to a 1, which is a 100% chance of detecting the effect, as a function of the number of studies, that's on the x-axis, and the amount of power in each study. So let's say each study is actually adequately powered. Each study has 80% power, which is not the case. Very few studies are adequately powered. But even if each study was adequately powered, if you have 1 study, your paper has 80% power. If you have 2 studies, it drops to like 65%. 3 studies, by 4 studies, you're already at 40% power. That means the chance that you would get 4 significant results in a row if each study was powered at 80% is only 40%. If you go down to 6 studies, we're now at 25, 30%. And that's if it's 80%, if each study is powered at 80%. Each study is not powered at 80%. On average, they're probably more like 50, 65%. So take a 3-study paper where each study has 65% power. You're now at 30% total power. The chances that you would we're assuming the effect is real. We're assuming the true population effect is not 0. It's different from 0. If each study has 65% power, your paper, that string of studies should only have a 30% chance of having 3 significant results. One of those should, by chance, just not be significant. If you have 4 or 5 studies, it's getting pretty low. If you have 6 studies and they're each underpowered and they're all significant, that's very fishy. That's extremely improbable. So Uli calls this the improbability index, which is basically if you see a paper with a lot of studies, they're each underpowered, and they're all significant, that's fishy. Now, if they have 6 studies and 5 of them are significant, that looks a lot better, ironically, because that's what you would expect. If each study only had 80% chance of detecting the effect, if it's there, 1 out of 5 should not detect the effect, right? It shouldn't be statistically significant, even though the effect is real. So a string of significant results, if each one is based on a small sample, is fishy. So putting 2 and 2 together, most papers have multiple underpowered studies, or at least 1 underpowered study, and many have multiple underpowered studies. Almost all of them are significant. It's rare that you'll see even 1 out of 4 or 5 studies not reach significance. And a string of significant underpowered results is extremely unlikely. And we see it all the time. So what's going on? This is where p-hacking comes in. So as we started realizing that this is going on, people started talking about researcher degrees of freedom, which is things that researchers can do during the analysis stage to kind of push their p-value down. If it's, let's say you do your analysis and it's 0.06 or 0.07, you're like, oh, damn, what can I do? So that's where researcher degrees of freedom come in. I'll talk about what those are. Questionable research practices is taking advantage of those researcher degrees of freedom. I'll talk about those. And the result is p-hacking, which is getting your p-value to drop below 0.05 so you can publish, which leads to false positives, right? Some of those are not true results. You should have accepted the null, and instead you hacked your p-value down so that you could reject the null. And that leads to a replicability crisis, the feeling that maybe many of our published studies are not replicable, maybe they're not reliable. Okay, so what are the researcher degrees of freedom? This is the paper I mentioned that was published in Psychological Science by Joe Simmons, Leif Nelson, and Yuri Simonson in 2011. So they identified several different practices people can do that inflate rates of false positives. So one is checking your data as they're coming in. So you're running participants and you run 20 people per cell and you're like, oh, let me see if it's significant now. So you analyze your data, oh, it's not quite significant, let's run 10 more people. And then you check again. It's still not quite significant, run 10 more people, check again. That hugely inflates the rate of false positive. Because if you think about like the Jeff Cummings simulations, right? There's a lot of variability in where your effect size estimate is going to be. And if there's no effect in the population, if the true effect size is 0, it'll still fluctuate around 0, right? And the more you check the data, the more likely you are to capture a random fluctuation away from 0 that turns out to be statistically significant. And if you stop there and you say, okay, that's my conclusion, I want that conclusion, right? That inflates a false positive rate. If you give yourself a bunch of chances to capitalize on chance and detect a significant effect, when in fact there is no, the real effect is 0, you're inflating your false positive rate. Now, that doesn't mean you should never check your data. There's definitely circumstances where it's fine, but what you should do is be transparent about it. If you checked your data, say that we ran 50 participants, we checked the data, we decided to run 50 more. You can even do a correction. You can correct your p-value for the fact that you checked your data. And if you are going to check your data, just do it once and have a good a priori reason why you're going to do it. So sometimes people are using new materials they've never used before, and they want to make sure that things aren't just completely fluky, and they don't want to waste 200 participants on these new materials if they don't work at all. Right? So you might have a good reason, but don't check multiple times. And if you do check, say that you checked, and maybe even correct your p-value, but at least be transparent about it. Or if you can afford to, just don't check at all. I think that's the best solution. You see a lot of covariates in analyses, so you'll see random papers that are like not about gender at all, that will throw in gender as a covariate. What's going on a lot of those times, maybe not a lot of those times, but one tool people do use to get their p-value below 0.05, they do their analysis without any covariates. It's not significant. They say, oh, well, maybe gender is adding noise in there, so we'll throw gender in as a covariate. Maybe it is. Maybe that's a good thing to control for, to add in as a covariate, but maybe not. And again, you're running the risk of capitalizing on chance, because the more analyses you do, the better the chance that one of them, just by fluke, will reach the p less than 0.05 threshold. And if you just pick that one and publish that one, that can be very misleading. So covariates are not always bad, right? None of these things are always bad. If you have a strong theoretical reason to include a covariate, absolutely, it's fine to include the covariate. But if you're doing it haphazardly after the fact to try to get your p-value below 0.05, that's bad. If you really believe that, in retrospect, it makes a lot of sense that I should have controlled for gender, I didn't think of that before, but after I did it, it really makes a lot of sense, then just be transparent about it. Again, say, initially we ran analysis without gender as a covariate, the p-value was 0.08, and then we added gender as a covariate, the p-value dropped to 0.04. Here are some theoretical reasons why in hindsight it makes sense. If you can replicate it, even better, right? So then the second time when you replicated that, then you have an a priori hypothesis that gender should be included as a covariate, and then that's not problematic. Dropping outliers. So again, it's totally fine to do, but it's much better if you have an a priori rule about which outliers you're going to drop. So you might decide ahead of time, okay, anybody above or below 3 standard deviations from the mean on each of my variables, we're going to drop, right? Then decide that a priori. If you start doing your analyses and then you're like, oh, what if I drop this person? What if I drop that person? Then you're capitalizing on chance again. Dropping measures or conditions. So you might measure one of your variables in 3 different ways. You're not sure which one is the best measure, and then you just use the one that works, right? That gets a p-value below 0.05. Again, you're running the risk of capitalizing on chance. Sometimes people drop entire conditions. They might have 2 different control conditions. They're not sure which one will work better, etc. And I think a lot of times people do these things innocently, not realizing that it inflates the false positive rate, but it really does, especially when you do them in combination. Generally running lots of analyses, so doing it with and without the covariates, with and without the outliers, with and without the different measures, et cetera. The more analyses you run to look for one effect, the more likely you are just to capture a random deviation that's not a true effect. And then this is a really problematic one, running lots of studies. So you guys have all heard of the file drawer. It's where psychologists put their studies that don't work, that don't get a p-value less than 0.05. So the one way to get a 6-study paper where all 6 studies are significant, even though each of them is not very well powered, is to have run 30 studies. Right? That seems like a lot of work, but now with MTurk, it's not that hard. Right? So there's a lot of controversy about whether it's okay to have studies in the file drawer and submit a paper with just the significant results. We teach our students to do that to some extent. We don't want to bog down every paper with all the failed studies. And sometimes there's good reason why the failed studies didn't work. Sometimes, a national disaster happened that affected people's mood and your study was about mood, or different things happened that led you to decide that that study was not a good test of your hypothesis. So sometimes it's fine to drop studies, but we know about motivated cognition. We know it's easy to talk ourselves into why, oh, well, that study, that was at the end of the semester, people were stressed. And that was at the beginning of the semester, people were whatever. So you can come up with all kinds of reasons to drop studies. So I think it's very, very risky to rely on your own rationalizations about why it's okay not to report this study or that study. I don't know what the solution is because we're so far away from being totally transparent about this. The psychology literature would look so different if people reported all their failed studies. And we'd need a lot more pages in our journals. We would need, readers would have to have a lot more patience. I don't know, maybe putting them in supplemental materials or having a footnote saying, oh yeah, for these 5 studies that worked, there were 2 that didn't. And now that we know, if we think about this idea of total power, that would actually make the paper look stronger. If the authors admitted that, yes, we had 5 studies that worked and 2 that didn't, and you could even do a meta-analysis of those 7 studies and show that there's a reliable effect. The 2 that didn't don't ruin the whole story, right? In some ways, they make the story more believable because there's noise, right? You're going to get some negative results, even if the effect is true. Okay, so questionable research practices. Leslie John and her colleagues did a survey where they asked social and personality psychologists, I think actually beyond social and personality, other psychology researchers, how often they did these different practices. So reporting only studies that worked, 50% of people said yes. I think this is a huge underestimate. Harking, so this is hypothesizing after the results are known. This is you run a study, you get an unexpected result, and then you write it up as if you had predicted it. There's a famous paper by Daryl Bem called How to Write an Empirical Article, which is a beautiful, beautiful paper. I used it when I taught research methods. It teaches people to do this. It says, we don't want to hear what you thought going into the study. We want to hear the best story you can tell now that you know the results. That's problematic, right? If part of the believability of your results is based on the idea that you had this theory a priori, that's part of what lends credence to the results, then faking that is wrong, right? That changes how people interpret your results. So I don't believe that only 35% of people arc. I mean, we literally explicitly teach our students, like almost everybody I know who teaches methods used to assign the Daryl Bem paper, and it says to do this. Checking data, so as it's coming in, 58%. Not reporting all your measures, 67%. Selectively dropping outliers. So this is, again, not a priori rules, but selectively dropping outliers. Most people thought these practices were possibly or definitely okay. And a lot of people do them. And again, we used to teach people, and many people still teach people to do these things. Okay, so if you're reading a paper, how do you know if something is p-hacked? How do you know if people use these methods to get to p less than 0.5? I want to emphasize you can't know for sure. And I think it's very risky to ever accuse a specific person or a specific paper of being p-hacked. I'm not saying it's never justified, but I personally wouldn't do it. So if the p-values are consistently very close to 0.05, if you see p-values of 0.04, 0.045, 0.048 over and over again, that's a sign. And now the Simmons, Nelson, and Simonson have a new technique they call p-curving, where you make a graph of an individual researcher's p-values or a paper's p-values. If you have a few of them, you can see how close that set of p-values is to 0.05. If there's a bunch right below 0.05, that's suspicious. I think small sample sizes, to me, are the biggest red flag. If you see consistently small samples, especially a string of many studies, all small samples, all significant. Again, unless you're dealing in a sub-area where there's huge, very reliable effects, like visual perception maybe. But in most messy areas, like social and personality psychology, this would be very fishy. Interaction effects are great, but you need even more power to detect an interaction. Interaction effects are smaller than main effects. If you have a three-way interaction, that's going to be even smaller. So if someone is getting significant interaction effects consistently with small samples, I'm suspicious. If you see covariates that don't make a lot of sense, and they're different from study to study, so in one study they control for gender, in another study they don't, and it's the same theoretical framework, that's a little suspicious. But again, not all covariates are suspicious. Excluded participants, again, if they say, 16 participants were dropped and they don't say why, and the best thing is if they say we had an a priori rule that we would drop anybody who didn't pass the manipulation check or anybody who scored 3 standard deviations above or below the mean, etc., then it's fine. But if it seems haphazard, that's a red flag. If they have multiple dependent variables and they seem like they're inconsistently reporting them, so I've seen cases where people use a well-validated 20-item measure, and then they say, oh, we dropped 2 of the items because the scale is more reliable that way. I think if it's a well-validated, widely used measure, you don't just drop 2 items. It doesn't matter if the reliability is a little bit better without those items. You use the full scale, and it seems fishy if you just selectively pick some of the items. Even if you say, well, it has better reliability, I don't know that that wasn't a post hoc decision to look for some reason to drop those items. And then I think, we don't focus on this enough in psychology. Believability matters, right? I think that the believability, the a priori plausibility that taking Tylenol could reduce your response, your compensatory affirmation in response to a threat, that matters, right? Like if you're going to tell me that that's a huge effect as big as, or it's a medium effect as big as the gender difference in weight, I want some convincing. I want more evidence than if you're just trying to convince me that people who like spicy food prefer Indian food. If we weren't streaming, I would give you more examples. Okay, so I'm going to skip this. The reasons we do these things is because we need to publish and we need to get tenure and so on, and editors want neat and tidy results. I think that's bad. I think editors need to be much more tolerant of messiness. Editors need to realize that if you have 4 studies and one of them is not quite significant, that's actually a good thing. But that's changing slowly. So some solutions, journals are adopting new article submission policies. So the APS journals are passing new submission guidelines. Personality journals are as well. SPSP is just published a best practices article. Hopefully that'll lead to new submission guidelines for their articles. So one is a declaration of research practices, so more transparency, asking people to say, did you run other studies that didn't work? Did you have other measures in there that you didn't report? Did you drop people that you didn't a priori decide you would drop, and so on? This is, again, Simmons, Nelson, Simonson proposed this 21-word solution. They want everyone to include this statement in their papers. We report how we determined our sample size so that you didn't just check and then stop when it became significant. All data exclusions, so any dropped measures, any dropped participants, all manipulations, you didn't just drop a condition or drop a manipulation, and all measures in the study. So they're not saying you can't do these things. They're saying if you are going to do these things, tell us that you did that, right? Let us evaluate the plausibility of your result with the full information. Journals are now focusing on reporting effect sizes and confidence intervals, not just p-values. I think this is a really important development. One thing I would note is that people have jumped on the effect size bandwagon, which is great, but effect sizes are not very useful without confidence intervals. You really need both effect sizes and confidence intervals. And the reason is, so the reason you see a lot of fMRI research, for example, with huge effect sizes, is because with fMRI research, you almost always have small samples. It's just too expensive and too time-consuming and so on to run large samples. And with a small sample, the only effect you're going to detect at p less than 0.05 is a huge effect. Right? If you have 10 or 20 people in your study, the only effect that's going to be statistically significant is if it's huge. If it's close to 0, it's not going to be statistically significant. So that's why the only things that get published in fMRI research have huge observed effect sizes. I think that's a huge inflation of the true effect size. I don't think that fMRI results are necessarily that much bigger than behavioral results, but that's what you see. And if you don't include the confidence interval, it looks like, whoa, look at that effect, it's huge. But if they had the confidence interval, you would see that it goes all the way to 0.05, right? From D of 0.05 to D of 3 or whatever. So you have to see the confidence interval, because otherwise people get credit for huge effect sizes that they really shouldn't get very much credit for, because there's no precision around that effect size estimate. Right? You want to know not just where the point estimate is, but how precise it is, how much confidence we should have in that point estimate. If it's really big, but there's a huge confidence interval, then okay, maybe yeah, they get some credit for being able to exclude 0. That's great, good, you got a significant result. But you can't tell us that it's large. You really don't know if it's large or small or medium. So confidence intervals are really important. And then attention to sample size. So for example, the Journal of Research and Personality will now reject outright any paper with less than 100 people in their sample unless you have a good reason. So maybe, if you say you're doing fMRI research, it's just too expensive to get 100 people, or you're studying a clinical sample, or whatever. There are good reasons why small samples are sometimes necessary, unavoidable. They're never good. It's never a good thing, but sometimes they're unavoidable. Sometimes if you want to study this phenomenon at all, you have to tolerate small samples. And I will tell you something that you'll know more than some editors if you remember this. There's no downside to a large sample. There's nothing bad. There's no way in which a large sample is bad or worse than a small sample. It's only better. You only have more evidence and more knowledge. That seems obvious, but I've now seen 3 different editors reject papers partly on the basis that they had too much power or too large of a sample. And the editor of Nature Neuroscience published an editorial where he said that one of the benefits of having small samples in neuroscience is that we only detect important effects, because with our small samples we can't detect trivial effects. At least any effect we do detect has to be important. It has to be large. Of course, that's false, because they could detect some effects that are in reality are small. They just observed a large effect in their sample with a huge confidence interval. But that misconception comes from the idea that if you only look at p-values, then yes, if you have 1 million people in your sample, which sometimes you get, right, especially with online studies and so on, then even an effect of D of 0.02 or something trivial like that could be significant if you have enough people. So if you only look at the p-value, let's say I tell you, guess what? Women are, I don't know, better at taking care of plants. I'm just thinking of plants than men. And I had a sample of 1 million, and I tell you p less than 0.001. Well, that is misleading, because you really want to know the effect size, right? When the sample is that large, the p-value tells you nothing. But that's a good thing. That's because you have so much power that everything's going to be significant. Everything's going to have tiny, tiny confidence intervals. So none of those confidence intervals include 0. Very rarely do they ever include 0. But that's only a disadvantage if you only look at p-values. If you look at the effect sizes and confidence intervals, you're not going to be misled. Right? So if I tell you women are better at taking care of plants than men, D equals 0.02, you can evaluate whether that's a meaningful difference. So it's reliable if the confidence interval is narrow. I can tell you it's a real effect, but maybe it's totally practically insignificant, right? So large samples are great. Yes, you do have to pay attention to the effect size and the confidence interval, but we should always be doing that anyway. There's no downside to large samples except that they cost more money and take more time. But that's any good research practice will probably take time and money. Tolerance of messiness and marginal p-values. So again, this is really editors need to come around before anyone else can. I don't encourage you necessarily to report. I don't know what to say you should do. Whether you should report failed studies, whether you should report all the messiness in your results and your data. I think that would be great, but you will be at a disadvantage in publishing until editors come around and value those things and don't want just the most beautiful, polished story that you could tell. Another really important movement is encouraging replication studies. So APS has a mechanism for submitting replication studies. More and more journals are explicitly saying we will consider replication studies. Replication studies need to have large samples. Again, all studies should have large samples, but again, especially if you anticipate getting a null result, in order for that to be meaningful and convince people, you need a large sample. And also, if you get a different result than the original study, in order to know which one to believe, right, you're going to have more weight to your evidence if you have a larger sample. Okay, so I think a kind of bigger picture thing is this idea of meta-analytic thinking. That we should think of each study as just grist for the mill, adding a little piece of evidence to the pile. And no one study is conclusive, and with each new result, our overall estimate gets more precise, and each study is given weight according to its sample size. right? The studies with larger samples get more weight in this kind of averaging or meta-analysis. So here's a picture of a meta-analysis. This is a cumulative meta-analysis. So we recalculate our estimate and our confidence interval with each new study. So you can see the confidence intervals shrinking. This is an odds ratio, so 1 is no effect. So this, over time, we get more and more confident there's an effect. I don't even know what this is. I just found it on Google Images. But the idea is that with meta-analysis, we get a more and more precise estimate, and each new study just adds to that overall estimate. I think it's a really good way to think not just about a literature, but even about an individual study. But it's just one piece of evidence. The larger the sample, the more weighty that evidence is. And then overall, I think on the research side, I think we need to move away from null hypothesis testing and p-values and focus on power, effect sizes, confidence intervals, meta-analytic thinking, more transparency, more tolerance of messiness. I think we need fewer papers. We need to run fewer studies and use those participants together in one study and have a larger sample. I do worry, and when I advocate for larger samples, that people will then just start doing only vignette studies and only MTurk studies, and that I would hate that. So intensive studies like behavior coding and longitudinal and physiological stuff, those are wonderful, wonderful things. So if we want larger samples and we want to keep that variety and diversity of methods, we're going to have to accept that there's going to be fewer papers. People are going to publish at a less crazy rate than they currently do. But I think that would be a good thing. And as an editor, I know we can't even find enough reviewers to handle all the papers coming in. So we need to slow down anyway. So I think that would be a good thing. And again, Nelson, Simine, Simon, they've written a lot about these issues. One of them is let's publish fewer papers.
We have 15 minutes till the next talk. I maybe would suggest we take 5 minutes for questions, and then if there are more questions than that, people can just ask you during the break. Anyone have any questions that they want to ask now?
Sorry, so I don't have much experience in this stuff. Could you just emphasize a bit more the distinction between harking and allowing your theory to emerge from the data?
So the question is, what's the distinction between harking and allowing your theory to emerge from the data? I think the difference is, if you hark, you stop there. So you get a result, you say, oh, that's interesting, let me build a theory around it, and then you publish that. Allowing your theory to emerge from the data, you would then do another study to test that new theory. And then it would be more okay to admit, we did this study, we got this unexpected result, so here's how we explained it. And then we did another study with that a priori hypothesis to test it. And I would like editors to be more tolerant of that story. But if you just stop with the conclusion and you never test it with that a priori hypothesis in your head, then I think then it's harking.
Okay, should we take a break? So we'll get back together at 11.